So now let's play a thought experiment, a fun thought experiment, okay? And so I'll remind you about STP. Okay, STP says, just really quick before we start this thought experiment, STP says 273.15 Kelvin. It says 1 atmosphere, and it says 1 mole of gas occupies exactly 22.42 liters per mole for 1 mole of gas. Okay? So here's our thought experiment. Suppose now we take 2 containers. So we're going to say this is experiment 1 and experiment 2. Okay? So first let's do experiment 1. We take a container, and the container is, just bear with me, this is why this is a thought experiment. I'm going to erase that because it's hard to see it. The container is exactly 22.42 liters. Okay? And maybe it's 22.4156789 liters. It's exactly 22.42, whatever it needs to be for STP. And I put exactly 1 mole of helium in that container, and I get the container to be exactly 273.15 Kelvin. What is the observed pressure? So that's experiment 1. Experiment 2 is the same experiment 1, but now instead of helium, we put water. Okay? I want you to think about this. Pause the video and think about this. And I want your answer choices. I'll give you 3 possible answer choices. Answer choices are P observed equals exactly we'll say to 3 significant digits, 1.000 atmospheres. That's one possibility. Other possibility, P observed is less than 1 ATM. And your third and final possibility, P observed is greater than 1 ATM. So what do you think it's going to be? Think about it. Okay? Pause it if you have to. I'm going to fill in the answers. As it turns out for the helium case, it would be 1.000. Okay? Because think about it. All we've done is just recreated STP. Right? If it's 22.42 liters and we've put 1 mole and we've said it's 273.15 Kelvin, it'll be 1.000 ATM. But now what about the water? And the other thing that I'm going to say about this, we're going to assume water doesn't freeze. Because as it turns out, 273.15 Kelvin is 0 degrees Celsius, so we know water would freeze at that temperature. But in this thought experiment, let's assume water doesn't freeze. Okay? Well, as it turns out, this P observed, let's see, I have it right here, it would be less than 1 atmosphere. It would be 0.989. I don't expect that you'd be able to get to that 0.989. That's why I said, think about it, is it less than 1 or is it greater than 1? So what's happening with this thing? Okay? Well, as it turns out, and we've talked about this before, in the water molecule, the hydrogens are just slightly positively charged. That's what this little delta means, slightly partially charged. And the oxygen is slightly negative. Okay? And ideal gases, they don't interact with each other. They don't experience positive and negative charges. At least that's in the ideal gas law. But in reality, gases do interact with each other. They do feel positive and negative charges. Okay? And notice here I drew this oxygen pointing to the hydrogen because since the oxygen on this molecule is slightly negative and the hydrogen on this molecule is slightly positive, negative and positive will attract. Okay? And so what that means, these water molecules will influence each other more to collide with each other instead of colliding with the walls. And we noted that pressure is a result of collision with the walls, right? So if these water molecules are influencing each other to suck in a little bit more, but I'm forcing this container to be 22.42 liters, then that means the pressure will be slightly less than 1 atmosphere. And we get that from the van der Waal equation. Okay? So this is this chunk of the van der Waal equation that I pointed out. That's the correction. So P ideal would equal P observed plus this correction term. And so now look, I've got all of these various gases, and we've set the ideal pressure. We've said the ideal pressure will be 1.000 for each of them. Okay, so really, as it turns out, this A term gives us the ability to attract other molecules or atoms to itself. Okay, and as it turns out, the bigger this A term is, the more interaction a gas will have with itself. So look at the helium case. That A term is small. So that should be, the units of that should be atmosphere liter squared per mole squared. So that got cut off. So A has units of ATM liter squared divided by mole squared. So that's the units of A. So A would be for helium 0.0341 atmospheres times liter squared divided by mole squared. So it's a crazy unit, I realize, but what's important to me that you understand is the size of this A constant. Look, for helium, it's tiny, and so that means your observed pressure would be identical to your ideal pressure. And then now look, neon is also similar, 0.211, okay? But look what happens as the gases get bigger. Argon, krypton, xenon, look, their A terms are actually kind of big. And look what happens to the observed pressure. It actually is decreasing noticeably from that ideal case. Okay? Because as it turns out, these gases, they have a lot of electrons. And those electrons can kind of slosh around in the molecule a little bit to temporarily attract other molecules. So for example, if I have a big old xenon, okay, and it gets close to another xenon, then what's going to happen is as they start to approach each other, so I'll draw this like as they are colliding, okay, then all of the electrons on, and it doesn't matter which one it is, but let's say all the electrons on this xenon will get repelled by all the electrons on this xenon. So it'll force all of those electrons like to the other side. And then now what you'll have is a slightly positive side of this molecule or atom and a slightly negative side. And then a slightly positive side and then a slightly negative side. Okay? And that actually becomes noticeable for the heavier atoms, the atoms that have lots of electrons. And it's noticeable in the fact that you would actually observe a decreased pressure relative to the ideal case. And now if you look at these molecules, chlorine, carbon dioxide, methane, ammonia, water, it's a very noticeable effect for them. Okay? Like water, 0.989, because of its ability to attract due to hydrogen bonding. Okay, so now what about the volume of the molecules themselves? Well, if you look, our ideal volume is 22.42 liters. Okay? So our observed volume would actually have to be bigger. And the observed volume has to be bigger because the molecules take up volume themselves, right? So it's got to be bigger because if you think about the algebra, right, if I add NB to this side and add NB to this side, right, it's increasing that ideal volume relative to the observed case. Okay? And we note that helium is quite small, neon is quite small, but as we go down this list, the gases are getting bigger, as you can see by this B term, okay? And you notice that the observed volume, right, is getting bigger. So these effects of the molecules occupying real volume and the molecules being attracted to each other, they're opposites, okay? The attraction of molecules has a way of reducing the pressure, whereas the volume, what did I say there? The attraction of molecules to themselves will reduce the pressure. The volume of the molecules themselves will increase the volume, okay? All of that being equal, when you consider both of those effects in the van der Waals equation, you get a very accurate determination of pressure or volume or temperature of moles of gases. Okay, and you'll only have to do, I think, like one calculation on this in your homework. More important, what I want you to understand is kind of related to this idea, right? When we consider that molecules can actually attract themselves to each other, it reduces the pressure. When we consider that molecules actually occupy real volume, it will increase the volume of our sample.